Okay, here are second examples of data provided by tensile tensile test, meaning we put samples of steel in this case and pull on it, and we record some data. The data that were recorded are usually the data that are recorded with the machine directly, meaning the elongation. So how far the two attachment to the samples went away. So let's say at the beginning this is 0, and when we pull on it, it's increased 0.01 millimeters, 0.1, 0.2, etc., etc. So this is the elongation that is recorded. And there's a load cell that records the force that is required to create that elongation. So usually, especially for this one, I guess that the driven information is the elongation. So we are pulling with the constant distance, with the constant elongation, and we record the load, the force needed to achieve that. So parentheses close, what is provided is the elongations and the load, and what we want, remember, we want the strain. So in this case, that will be millimeter per millimeter, and we want the stress, and the stress will be, in this case, in MPa, because we are in international units. So let's find those information first. So we will fill that table. I like that, it looks nice. The strain, that will be your elongation, divided by what is provided is our uh, length not, the initial length, the 50 millimeters. So enter. And I will drag this formula, but before dragging this formula, remember in Excel, if we want to block an absolute value, so the length not, the 50 millimeters don't change. Okay, so we want to block this cell B18. So we add the $sign. Oops. Oh, what happened? Dollar and dollar. In fact, you just have to block the 18 because we will drag it down. But here we go. And after that, we click enter. So we have the strain for this first data, for these elongations, etc., etc. And you see, we always divide by the 50. Let me try to show you the, I need to put on more. Yes, okay. Let me do something very quickly. You will see. I think that will be easier to see it. Up, up. Here we go. And maybe 125, so you will see better. Here we go. You'll see a little bit better the formula inside. So always the elongation divided by the 50 millimeters on the bottom there. Okay, I can do something to delete so it's a bit closer. So now for the stress, the stress that will be the load divided by the area. What is provided in your instruction will be the diameter. Okay. Oh, I cheated there. I already found the area. So my area will be, let's look at this formula, pi times the diameter divided by 2, the radius square. So I found the area of these samples. It's provided that it's a circular sample. So what I need to do is I need to divide the force, the load, divided by the area in millimeter square. Enter. And don't forget, the area also will not change. So I want to block this B16 cell. So I add the $sign in front of it and enter. So now I have the strain and the stress for each data recorded. Let me put this also in the middle and some up bold one. Here we go. Up you can see everything. No, there's a lot of numbers after that. Let me just check one thing. Are we in megapascal or we are not in megapascal there? Those data looks a bit smaller because we are in kilonewton. We need to multiply by 1,000. So add the time 1,000 and drag again or double click on the top right there. Okay, my double click doesn't work, so let me drag it. Here we go. This is the stress in megapascal this time. Up, I will put maybe just 10, and the strain is fine like this. So now I can plot this curve because I have a strain and stress. Remember, include your first row and click Insert, Chart, and we can have, oops, up, move up, area chart, line chart, the smoother chart that looks a bit smoother. Um, doesn't matter too much. I would say what is important is add series the data label there. So we can see which part is elastic and close. So here we go, we have all data. We can move a little bit the up the label. Okay, it's out because I don't have my mouse. Okay. Anyway, you see it. So now the question are, what is the Young modulus? And we have to find some maximum yield strength, fracture, and things like that. Let's start by the Young modulus, because that will be easy to do it in Excel. Okay, it's provided that the linear part of the curve, the elastic part, is up to the second point, so up to the stress that is equal to 260, 250, no, 260, 259.9, so 260. So we will use the delta from 0.4. So we will use the delta between this one. I will highlight them so you can see them. We'll use the delta, those data for the delta. So Young modulus will be ups the delta y. So we go from 0. So we can just use this one divided by the delta x. So that will be in MPa. And you see MPa usually give you very big value. So let's find it in GPa. Gigapascal, not GPa, and we divide this one by 1,000. So the Young modulus of the steel with this graph give us 216 gigapascal, that value. So this is for the Young modulus. After that, we need to find the ultimate stress. The ultimate stress. The ultimate stress on your graph, and that's where it's important to have the label. Okay, let me put it a little bit bigger just for this one, and we don't need the data to the right, so we need the stress, strain, and the graph ultimate stress will be this one, the maximum stress that we reach. So let's put that the ultimate stress, and we just measure it. That will be the largest value that we get, and the largest value that we get was the 525.6. Or you can use the formula, the max of all those values if you want. Okay, and this is MPa. We need the fracture stress. So the fracture stress is the very last value of the stress of your sample. So that will be this one, the 479.1. This is equivalent on the graph. Oops, it's MPa. On your graph, this is this point there, 479.1. This is where your sample break. Usually it's break and you have a drop in the load, goes to 0 in the next instant. And the last value that we want is the yield strength. So yield strength at 2%, 0.2% yield strength or stress. Okay. So for this one, what we need to do is like we need to draw a line that starts at 0.002, so 0.02%. So that will be very, very close to air. Okay, so because this one is 0.002, so very, very close to air, and we draw a line up to there, and we find the yield stress, okay, or strength. So that will be the limit that we will use, so we are sure that we stay in the elastic zone. Just a little bit after, but almost we stay in the elastic zone. We don't start to create a permanent deformation to your sample. So if I don't think I can draw a line there, but I will draw it on the slide. So very, very close, 0.002, because we are at 0.2%. Okay, so very, very close. And let's say maybe we will cross. Okay, this one was 260, so it has to be a little bit more than that one. Maybe let's put 265. 265 MPa. Oops, 265 MPa. So remember, it's a line. So this one is 0.025. We need like 10 times smaller than that, like very, very, very small and parallel to that. So, oops, this is the value that we found. Let me marking a little bit so you can see them. We found a Young modulus of 216.6 gigapascal, ultimate stress value of 525 megapascal, a fracture stress of 479 megapascal, and a yield strength of 265 megapascal, so quite small compared to the ultimate stress. I hope that makes sense. Let me know if you have questions. Bye-bye.